Hello and welcome to our next Extension 2 lesson. Today we're going to be dipping our toes into physics a little bit, and we're going to be looking at forces and equations of motion. I'm assuming that you have a very basic knowledge of physics. If you know more than what I'm doing, well then that's fine. If, however, I'm assuming that you know stuff that you don't, please let me know. All right, that aside, let's get into it. All right, so Newton's laws of motion. I'm assuming that you've covered these, but again, let's just go over them very quickly. So law one, an object is going to remain either in uniform motion or at rest unless there's some external force that acts upon it. So we've got our person in the car hits the wall and stops, but that person keeps moving because they haven't been stopped. Right? The car's been stopped, the force has acted on the car, but not on the person, so they've been flung over the top. Law 2, for any constant mass, force is going to be mass times acceleration. This one we're going to come back to several times today, so it's important that we know that one. And then law 3, for every action, there is an equal and opposite reaction. So that, for example, with our space shuttle there, it's got a chemical reaction occurring so that it forces the propulsion, forces out the back, which propels the rocket up. So that's the equal and opposite reaction. All right, it's pushing down, so the opposite reaction is the ship gets pushed up. All right, so a force diagram. This is where we draw all the forces that are acting on a specific object, and we're making sure that we state their direction and magnitude. There are going to be numerous forces that may be acting upon objects, or sometimes called particles. It's the same thing. First one, which was, I remember in high school, the hardest one for me to get my head around, was normal force. Right? If there's something that's just sitting there not doing anything, there is a normal force pushing that book up. Right? It was never explained to me that what it is the counteracting force of gravity. So gravity is pulling it down. The fact that it's not going through the table is exerting that normal force back up on that book sitting on the desk. Frictional force, well, there's obviously going to be any amount of friction that occurs between two items. Most notably, if you look at a road, alongside the road, there's like emergency stopping lanes, which are made of gravel. That has a higher level of friction so that it can slow you down, right? It resists your motion to help slow you down. So it's acting in the opposite direction to that motion. Air resistance force, well, that's a type of frictional force, but it's the friction that's caused from air rather than from a specific surface. Otherwise known as drag, it's the air resistance. Tension force, so that's what's transmitted through any sort of line. So that line could be a rope or a chain or a cable, doesn't matter what it is. But it's pulled tight by forces that are acting on both ends of that particular line, whatever it is. And they are pulling equally in opposite directions, right? That's what that tension is going to be. Now, the only exception to that is if we've got multiple things acting on that particular line, then the total tension will be equally opposite, but along the way there are going to be variations. And we'll kind of look at that a little bit. Applied force, so if we apply a force to something, we're trying to move it, right? So it's any force exerted on something in an attempt to move it. So if I'm pushing that book sitting on my table, not only is the normal force stopping it from going through the table, but I'm pushing on it. That's the applied force, me moving it. A spring force, so if we've got some sort of spring, we can either stretch that string out and it's going to want to go back to where it was, or if I try and compress it again, it's going to try and push out to where it originally was. So that spring force is always going to be the restoring force opposite to whatever force we've applied. All right, if you look at any particular spring, it's sitting in a state of happiness, shall we say. That's its equilibrium. It's not doing anything. As soon as I either try and expand it or compress it, I'm acting a force on it. The spring force is it trying to get back to that happy place, that equilibrium. Now, one thing I haven't mentioned with all of these, there are two different notations, well, except for the last couple there. So we've got, for example, normal force F subscript norm is saying it's a force that's normal, but it's also referred to as capital N. Right, that's the normal force. Likewise, frictional force, F is just for the friction, R is for air resistance, T is for tension. The important thing is to remember that those are all forces. So if we see R or F or T, we just need to make sure that we get that those are all forces. Likewise with N. Last one that I haven't mentioned yet is gravity. So obviously we all know what gravity is, but as far as the definition goes, it's the force of attraction between two objects. There's this great idea that gravity is something that's pulling us down. Well, technically that's wrong. Gravity is all based on the size of the object. Not only is the center of the Earth pulling us towards it, but we're also technically pulling the Earth towards us. It's just that our mass in relationship to the Earth's mass is so different. Ours is so teeny tiny small that that attraction that we're pulling on the Earth is insignificant. It's basically would round to zero, but it is still technically there. All right, so that's just a quick rundown of some of the forces. Most of those we will be looking at some point over the next couple of examples. All right, so example 1, we've got a car here and we want to identify all the forces that are acting on the car while it is driving on the freeway. Now I've got the 4 different colored arrows there representing the 4 forces that are acting upon the car. So the first one is our yellowy orange color pulling down. That's obviously going to be gravity, right? The car is pulling the Earth towards it at such a small rate that, like I said, it would just disappear and not be counted. So the resulting force is just a downward force being caused by gravity. What's the counteracting force to that that stops the car going into the Earth? Well, that's going to be our normal force. It's the force that is repelling us back up. We've got 2 other forces happening there. Obviously, if we're driving, we've got the applied force, right? We're applying force to this car moving forward. There's going to be 2 forces that technically are acting in reverse to that. What are the 2 forces that are going to slow us down? Well, we've got friction and air resistance. All right, so we would add those 2 together to find out, well, what's the combined resultant net force that is acting on the car. As we can hopefully see by the size of the arrows, the applied force is going to be bigger than the friction and air resistance, so we're going to have forward motion. If, however, all of those motions were equal and opposite, they would cancel each other out and our car would be remaining stationary. All right, our normal force and our gravitational force, those should hopefully cancel each other out. And our applied force is going to be bigger than our friction and air resistance, so we're moving forwards. But if they were exactly the same, we would be basically revving our engine and not moving. Example 2, identify the forces acting on these objects. So here we've got a skydiver. What forces would you expect to be acting upon that particular person? Well, obviously skydiving, they're going to jump out of something and they're going to fall down to Earth. So there's going to be this downward thing, and that of course is gravity. There is also an upward force. Not going to be a normal force though. Our upward force is going to be air resistance. Next example. Here we've got a pendant that is hanging around the neck. Now this is just a statue, but it's still got those same forces in play. So what are our forces? Well, again, we've got gravity pulling it down. That's not going to change. But this time what we've got is that chain is what's holding it. So from that particular point, we're just looking at the pendant, we're going to have 2 tension forces. Are going to be equally coming up both sides of that particular chain. All right. The resultant of those 3 forces is going to be 0. And they're going to cancel each other out, hence the pendant stays stationary. Third example, we've got a set of scales here. Now we could put something on the scales and then that little needle is going to move around to tell us how much things weigh. So again, we're going to have gravity pulling it down, but it's not going down at the moment. Why is it not going down? Well, it's actually spring loaded. There's a spring in there, so we've got that force of the spring pushing it back up. So again, those 2 forces should cancel each other out until we add in some extra weight on top of it, which will then pull down that top platform. And then, of course, our spring force would also have to increase. Okay, so resolution of vector quantities. So we've got some force, and we're going to call it F, and it's going to make some angle theta with our x-axis. Then F can be written in terms of components in the x and y directions. So we can see there, looking at our diagram, that our horizontal component is going to be F cos theta, and then our vertical component is going to be F sine of theta. The way that I try to remember these sorts of things is because theta is not always going to be an angle to the x-axis. In those situations, what I do is I remember that cos theta is going to be the side that's adjacent to where my theta is placed, and then sine theta is going to be opposite the angle of where my theta is placed. Right? It'll always make a 90-degree triangle. It's just remembering that the force is going to be our hypotenuse of our triangle. Sine theta is always opposite, cos theta is always adjacent. Now, this process of writing it in terms of its components is called resolving a force. So when we say let's resolve the force, or what is the resolution of these forces or vector quantities, it's just talking about identifying what is our x component and what is our y component. Okay, so example 3, we want to resolve horizontally and vertically the force F that makes an angle of 60 degrees to the x-axis. Remember, resolve horizontally and vertically, we just want to find what are the x component and the y component of F. So let's start out off with a diagram. So we're going to have a force making an angle of 60 degrees. So remember that opposite our 60 degrees is going to be sine, adjacent to our 60 degrees is going to be cos. So then our horizontal component is F cos of 60 degrees. Now, cos of 60 degrees, we should hopefully remember our exact value for that is going to be a half. So therefore, the horizontal component is going to be 1/2 of F. Our vertical component, well, that's going to be F sine of 60. Again, our exact value for sine of 60 is going to be √3 on 2. So we're going to get √3 on 2F. Right? We will always have enough information so that we can simplify something down. Right? It's rare that we would have to leave it in terms where we can't simplify it down. All right, so equilibrium. So for equilibrium to occur, this is where we want to sum up all of our forces together, and they should all cancel each other out so that we get the sum of all of our forces to be 0. So let's say, for example, we've got 3 forces, F1, F2, and F3. If we add them together and it equals 0, then we're in equilibrium. There is no motion. So here's an example where we've got a box on an incline. There are 3 forces there acting on that particular box, but equilibrium is being achieved. Nothing is moving. That box is staying stationary. So what we've got is that F3 is going to be the frictional force. So we'll give that a value of F. F2 is going to be our normal force. So that's the force that's stopping it from going through the surface. And of course, F1 is our gravitational force pulling down. Gravitational force being mass times gravity. Now we can go through and we can put in for F, third force there. It's going to have both a horizontal and vertical component, remembering that across from theta is going to be sine. So our vertical component there is going to be F sine theta, and our horizontal component will therefore be F cos of theta. That theta there obviously is going to be the same as the theta for our incline. Now we've done that for F, so we're going to do the same thing for N. Note that, of course, now our theta is up the top there. That angle is now from what would be our y-axis, not from our x-axis. But the side that is opposite that angle is still going to be using sine. So that one down there is n sine of theta, and our other side is going to be n cos of theta. So we've gone through now and we've identified the horizontal and vertical components for our 2 forces F and N. So horizontally, because we're in equilibrium and there's no motion, our horizontal components must be identical because they're going to cancel each other out. So F cos of theta must be the same as N sine of theta. Now I can rearrange that, divide both sides by cos, and we get that F is equal to N multiplied by sine theta over cos theta. And of course, sine theta over cos theta is going to give us tan theta. Now I can leave it just as sine theta over cos theta, and in fact we will be going back to that at some point. But that's horizontally. So now we can look at vertically. So vertically we've actually got three forces. Right? We've got both the vertical component of F3, the vertical component of F2, plus we have all of F1. So the vertical components of F2 and F3 are both acting upwards, and then F1 is acting down. So therefore our two positive ones going up must be equal to our one going down. So n cos theta plus F sine of theta must be equal to my gravitational force, mass times gravity. Now I can't remember if I mentioned it or not, but it is important to note that our gravitational force is different from gravity. So our gravitational force has the gravity acceleration as part of it. For example, 9.8 meters per second forms part of the force of gravity. All right, so we've got n cos theta plus F sine theta there. Well, we know F is n tan of theta. So I can just substitute that in, and now we're going to have n cos of theta plus n tan of theta sine of theta is equal to mg. Now this is what I was saying about how we're going to switch tan back into terms of sine and cos. So let's just get rid of that for a second. So we've got a bit more space. So I can pull out a factor of n as well. So we've got n outside of cos theta plus sine theta over cos theta times sine theta is going to be equal to mg. Well, on the bit there where we've got sine theta over cos theta times sine of theta, well, if I multiply that through, I'm going to get sine squared theta over cos theta. I want to do something with that cos theta on the left, kind of by itself there. What that really is a resultant of if I had, say, cos squared theta divided by cos theta, would give me cos theta. So I'm just going to rewrite it like that. Why might I do that, I hear you ask? So think of, we've now got two fractions there that are both over cos theta. So I can add those two fractions together. And what we're going to get is cos squared theta plus sine squared theta all over cos theta. Now, hopefully we remember that cos squared theta plus sine squared theta is going to be 1. So we get n outside of 1 over cos theta is equal to mg. So what I now want to do is I want to do a little bit of a rearranging, because our ultimate goal is to get that cos theta on the other side. We're going to multiply them together. Now we've got what n is equal to. N is equal to mg cos of theta. So we've managed to, starting off with a whole lot of forces, we've managed to get to an equation for what n is equal to. Now at the very beginning, when we were looking at our horizontal forces, and we had F cos theta equals n sine of theta, and we divided both sides by cos, what we could have done is we could have divided both sides by sine, and then we would have had n is equal to F cos theta over sine theta. And we could have gone through that whole same process, but what we would end up with is F is equal to mg of sine theta. All right, so it's the same thing we would have got just by, well, it's the same process we would have used to get through all of that to work out what n and f are. So the next thing we want to look at is our coefficient of friction, and that we use the letter mu, not to be confused with mu for the population mean. So we had that box on that incline when we had angle theta, and the friction was stopping it from sliding down the box. If we were to increase that angle theta, that box would eventually start to slide. All right, so there is a amount of friction that stops it from sliding, but once we get to that particular angle, that friction is no longer stopping it, and that's that particular coefficient of friction. It's that amount that is stopping that box from sliding. So when that object is just about to slide, right, that box is about to slide down the side of that thing, that friction there, at that particular point, is called the limiting friction. Right? It's the friction that is limiting that box from moving. But when it's in, just because the box is sitting doesn't mean we're at that point. We could increase the angle more and the box still won't slide. It's only when we reach that limiting friction point that the box will start sliding down the incline. So the magnitude of that limiting friction is always going to be in a constant ratio to the normal force that's holding it on to that particular surface. All right, so to work that out then, because it's always going to be in that constant ratio, our coefficient of friction is always going to be F over N, which if we rearrange it, that force of friction is going to be equal to mu times our normal force N. There are, however, two different types of our coefficients of friction. So there's the static coefficient of friction, which is when both of the objects are not moving. So if we were talking about our box on that incline, that would be the static coefficient of friction. If one or both of those objects are in motion, then we have what's called the dynamic coefficient of friction. We need to have at least one surface is moving. All right, so let's look at an example. So we've got an object that weighs 25 newtons in rough contact with a plane inclined at theta to the horizontal. It's just about to slide. All right, so we're at that point where it's about to start sliding. If the static coefficient of friction between the plane and the object is √3, find the angle of theta. All right, so it's talking about the static coefficient of friction. Neither of our surfaces are moving. All right, so where we want to start is a diagram. So there's our box on our incline. It's looking as it's about to slide down. What information have we been given? Well, we know its weight is 25 newtons. So m times g is 25. We don't need to know what its mass is. We don't need to know what the gravity is in this particular instance. We know its weight. It's important to note the difference between weight and mass. I'm assuming that would have been covered in physics, so hopefully you know what's going on there. What other information have we got? Well, we've got that the coefficient of friction is √3, but that's about it. We do know that this up here is going to be our normal force. And then, of course, we've got our friction over there, which we know is mu times n. Well, we know mu is our √3. Now, we looked at previously that n was going to be mg cos of theta. But like I said, we don't know m and g, but we do know that the multiplying m and g together is going to give us 25. So n, therefore, is going to be 25 cos of theta. Right? If we want, we could pretend gravity is 10, and therefore the mass is going to be 2.5. It really doesn't matter. The other thing we looked at was F was mg sine of theta. And again, we know that mg is going to be 25. So F is 25 sine of theta. But the other piece of information we've got is that F is mu times n, or U is F over n. How's that helpful? Well, we've just worked out what F and n are. So our mu of √3 is going to be equal to F 25 sine of theta over 25 cos of theta. Well, those 25s are going to cancel each other out. We're left with sine over cos, and of course sine over cos is tan of theta. So therefore tan of theta must be √3. So to find ourselves theta, we're just going to do the inverse tan of √3. And that tells us that theta is going to be 60 degrees. All right, so based on the fact that it's just about to slide, we can use that F equals mu times n, or that mu is F over n. And with all the other information that we've got there, particularly its weight of 25 newtons, we know that that angle must be 60 degrees. All right, so the next force we want to look at is tension. Now we've got two particular tensions here that are happening from where that weight is being suspended on our wire. Note that that particular weight is not in the center, so we're going to have two completely different angles being formed there. And as such, we're going to have two completely different tensions. All right, T1, the magnitude of T1 is completely different to the magnitude of T2. However, when we start resolving the horizontal and vertical components, those are going to start equaling each other. So if we look at horizontally, right, T1 is going to have a horizontal component and T2 is going to have a horizontal component. If we are looking at the angle from the horizontal, so where the cable would be until we put this weight on it, what we've got then is T1 cos of alpha is equal to T2 cos of delta. If, however, we were looking at the angles formed in the middle, or more or less from where that weight is being suspended from, where we've got there beta and gamma, rather than use cos, we're going to use sine. So T1 sine of beta is equal to T2 sine of gamma. Now it's totally up to, depending on the question, as to which set we want to use. Just remember about what I was saying before about which one is going to be opposite our angle and which one's going to be adjacent to our angle. So that was for horizontally. Now vertically, we've got three forces. We've got the two tensions pulling up, and we've got the gravitational force pulling down. So the two ups must equal the one down in order for them to cancel each other out. So vertically, we've got T1 sine of alpha plus T2 sine of delta is equal to our gravitational force mg. Or if we're looking again at those angles that are formed from where our weight is suspended, we're going to have T1 cos of beta plus T2 cos of gamma equal to mg. Again, it's really going to be dependent on the question as to which one is going to be relevant. So let's look at a question. So let's calculate the tension in this wire supporting a 60 kilogram tightrope walker, where the weight of the tightrope walker is at the center of the wire. It's going to cause it to sag 5 degrees. And we're going to let gravity be 9.8 meters per second. Note that we've got a mass of 60 kilograms here, not weight. All right, so that's going to be our mass is going to be 60. Gravity is 9.8. We're going to need to use those in order to work out what our gravitational force is. So let's start out by looking at horizontally what our components are. So we're using the angles that are formed coming down from the wire, so from the horizontal. So what we've got then is that T1 cos of 5 degrees is going to be equal to T2 cos of 5 degrees. Now, because then he's perfectly right in the center, the angles are exactly the same, therefore the tensions are going to be the same, right? This is the only time where those tensions are going to be the same, is if that person or weight is directly in the very center. So T1 is going to be equal to T2. So from this point on, rather than using T1 and T2, we're just going to say our force for the tension is just T. So that's for horizontally. Looking at vertically, remember we've got ourselves three forces here. We've got that T1 sine of 5 degrees plus T2 of sine of 5 degrees is equal to mg. Now, remember I said how T1 and T2 are the same. We're not going to use that anymore, so I can just replace those with T. So I've got T sine 5 degrees plus T sine 5 degrees. Well, that's just 2 lots of T sine 5 degrees is equal to our mass of 60 times our gravity of 9.8. So if I do a little bit of a rearranging there, I divide both sides by 2 sine 5 degrees, and we're just going to find there's our T, our tension force, all by itself. Type that into a calculator, and we're going to find out that our tension is approximately 3,373 newtons. Now that's for each of those two particular cables. Remember, T1 and T2 are exactly the same. Both of those will be just under 3,400 newtons. It does get a little bit confusing when we start using our normal force and newtons. That's something you're going to have to be mindful of. You'll see here that when I'm talking about the normal force, I've got N is italics. When I'm talking about newtons, it's just a straight capital N. My recommendations would be probably to write newtons out as a word rather than just using an N, just so you don't get yourself confused. All right, example 6. So we've got 40 newtons of force being applied to a 5 kilogram box at an angle of 30 degrees to the horizontal. If the dynamic coefficient of friction is 0.4, we need to find the acceleration of the box. All right, so it doesn't matter that it says it's the dynamic coefficient of friction, it's still just our coefficient of friction, so mu is going to be 0.4. The reason it's dynamic is because our box is going to be moving. Remember, one of our items is moving, therefore it's dynamic coefficient. So we've got drawn on our diagram there the force being applied of 40 newtons and our angle of 30 degrees. However, there are going to be other forces acting on our box, and we need to write them in. So firstly, we're going to have a gravitational force pulling it down, m times g. Now our mass of our box is 5 kilograms, but we don't have anything for g. Now, if the question is nice enough to not say that gravity is 9.8, Don't pick 9.8, be nice to yourself, pick gravity is 10. So let gravity be 10 meters per second per second. Now we can substitute in both mass and gravity. 5 times 10, our gravitational force, 50 newtons. Now, if we've got a downward force, there has to be an opposing upward force. That's our normal force. And of course, there's going to be some sort of frictional force acting on the box as well. So we've got all of our forces marked on there now. Now we need to actually go through and look at our components. So the 3 orange forces in there only have a single component, so we don't have to worry about anything there. Our red one, however, will have a vertical component and a horizontal component, so we need to look at those. We'll do the horizontal first, purely because the dotted line is there already. It's the side that's adjacent to our angle, so it's going to be cos. So remember, it's always going to be the magnitude of our force times the cos of our angle, so it's going to be 40 cos of 30. And if you remember your exact values for cos of 30, we're going to simplify that down to 20 root 3 newtons. That's our horizontal component. So now we want to look at our vertical component. If horizontal was cos, then vertical must be sine. So we're going to have 40 sine of 30. And sine of 30 is just a half, so that simplifies down to 20 newtons. All right, so we've got all of our forces there, so now we can actually start resolving them. Now I'm going to start vertically, and the reason for that will become clear in a second. So what forces have we got acting on our box in a vertical component? Well, we've got gravity pulling it down by 50 newtons, we've got our force being applied has 20 newtons acting up, and then we've got our normal force. Well, what's our normal force going to be? We don't have any value for that. Well, we can just find the difference of the other two, and that's going to be our normal force, because we're just at that point before the box moves. So at that particular point, just as it's moving up, we can change what our normal force is going to be. So our normal force is going to be 50 pulling it down minus the 20 pulling it up, means we've got 30 newtons. All right, so that's our normal force. And now all of our vertical ones are done, and we can move on to horizontal. Well, we've only got 2 horizontal. We've got the horizontal component of the force being applied, and we've got the frictional force. Well, friction, remember, is just going to be mu times our normal force. Well, we worked out our normal force just a second ago, which is why we did vertically first. And our mu is going to be 0.4. So we're just going to do 0.4 times 30, and that gives us 12 newtons. So that's our frictional force. Now we know we've got a frictional force of 12 newtons in one direction, and we've got 20 root 3 newtons in the other direction as part of our force being applied. So we want to work out what's the actual net resultant happening here when we factor in those two forces. The box is now moving, so it's not going to be in equilibrium. So what we need to do is find out what that difference is going to be. So our net force is going to be 20 root 3 minus our frictional force of 12. So our resulting force, 22.61 newtons, is what's going to be pulling it up on an angle of 30 degrees. Now, because our frictional force factored in our normal force, that's taking in both horizontal and vertical forces, that net force at the end there. Now, the question asks us to find the acceleration of the box. So remember Newton's second law, where we had that our mass times some sort of acceleration is going to give us a force. Right? So if we looked at our gravity one there, that g is the acceleration of gravity. It's our 9.8 meters per second, or in this example, we've chosen it to be 10. So the mass times the acceleration gives us the force. So we want to do that for the box. Well, we don't know the acceleration, but we do know the mass, and we do know the force. So our net force is going to be the mass of the box times the acceleration of the box. So we know that our force is 22.641, we worked that out. Our mass is going to be 5 kilograms, and then our x double dot is our acceleration. So I divide both sides by 5, and we get that our acceleration of the box is going to be 4.5 meters per second per second. Hopefully I've not gone over anything too quickly there, or there's anything in there that you're not being sure about. If you do have any questions at all, obviously, as always, send me an email or messages through Google Classroom. That works just as well. You've done that a few times. Either way, I will get the message and I will do my best to help. We haven't scheduled a Zoom meeting, so I might look into doing something about that. It's a little uncertain as to what's happening next week at this stage. Rumours are abound that we might be back at school, but you didn't hear that from me. So yes, any questions, let me know. Otherwise, I will talk to you when I next see you.